Hello everyone, I am Siddhartha Pramanik. I am a research scholar from the Department of Mathematics, IIT Kharagpur. This is the problem solving season for week 3 of the course Introduction to Rings and Fields. Before start solving some problems, uh, I will write down the keywords of the main topics which have been taught in the week 3. Meanwhile, if you have any doubt, you can put it in the chat box or you can unmute yourself and ask. Okay, so in the week 3, we have started with quotient rings, and then we have saw some isomorphism theorems. Particularly, we have saw the first isomorphism theorem, and we have also saw one important theorem known as the correspondence theorem. And we have saw some application of this also, mainly how to determine the ideals of quotient ring. Then we have saw one particular type of ideal known as prime ideal. Then we have saw integral domains. And finally, we have defined maximal ideals. So I hope you can recall all the topics. We will be solving the problems based on these topics only. Okay. So let's start with the first problem. So let R be a ring. Okay, then we can define the polynomial ring Rx in one variable. Now I will define a subset of the polynomial ring. Let let R be a ring and I be an ideal of R. Okay, now using this ideal I will define a subset of the polynomial ring. Define, let us denote this by Ix and define this as all those polynomials a0 plus a1x plus an x power n belongs to Rx such that the coefficients a0 an belongs to the ideal I. Okay, then uh, prove that Ix is an ideal of Rx and also we will determine the quotient. Further, so if Ix is an ideal of the polynomial ring Rx, so we can define the quotient ring, right? So what will be the quotient ring? So what will be Rx mod I of x? So we will see that it will be isomorphic to, you take the quotient ring R mod I first, then take the polynomial ring, means you attach the variable. So these two rings will be isomorphic. So I have taken a ring R and an ideal I. Then using the ideal I have defined an ideal in the polynomial ring Rx. And the target is to prove that if we quotient out Rx by this ideal, we will get a polynomial ring which look like this. Okay, I hope you have understood the problem. So there are two parts of this problem. First one, that Ix has to be an ideal, then we have to find this quotient. Okay, so I will do both at the same time. So what I will do is, so I will use the first isomorphism theorem. So let me define a map. Let f from the polynomial ring Rx to the polynomial ring R mod I of x be a function which is defined by, so just see that how the elements of this ring looks like. So the polynomials are a0 plus I plus a1 plus I x plus an plus I of x power n. I mean, the coefficients of the polynomials are the quotients, means are elements of R mod I. Okay, so you need just that observation. So how to define a function from Rx to R mod I of x? So define it, f of a0 plus a1x plus an x power n. You just take the coset which is represented by these coefficients. So you take just a0 plus I plus a1 plus I of x plus an plus I x power n. So this is the natural map which you can define from Rx to R mod I of x. So this is by using the natural map from R to R mod I. So we are just using that map. Okay, so now let's prove that this map is an homomorphism. In fact, it is an surjective homomorphism. So F is a ring homomorphism. So for ring homomorphism, we need to check three properties. Okay, let me write it here. So first one is it preserves addition. Second one is it preserves multiplication. And third one is it maps 1 to 1. So we'll check these three things one by one. So okay, let me write down clearly. You take two polynomials. Let px equals to summation ai x power I equals to 0 to n, and qx is equals to summation vi x power I equals to 0 to m, be two polynomials in Rx. So we need to check f of P plus Q is same as f of P plus f of Q, right? So let's see what happens. So then f of Px plus Qx. So this is basically f of summation. So what is Px plus Qx? So we will just add the coefficients component wise. So it is just basically ai plus bi of x power I. So I equals to 0, and the last term will be maximum of n and m. Now you apply the function f. So it will be basically ai plus bi plus I times x power I equals to 0 to maximum of n comma m. Now we are in the ring R mod I of x. So just use the addition of this ring. So we can separate it like this is summation ai plus I times x power I, where I is equals to 0 to n, and summation bi plus I times x power I is equals to 0 to n. So we are doing the addition in the ring R mod I of x. But this is nothing but you take the function f and apply it on p of x, and this is just f, you apply it on q of x. So clearly you can see f of x plus qx equals to f of x plus f of qx. So f preserves addition. So f will also preserve multiplication, but you just do it on your own in a similar manner. Also f preserves multiplication. So it is not difficult. You just have to use the multiplication of the both rings. So this one has been done. So the last one is 1 goes to 1. So f of 1 should go to then 1 plus I, and this is basically the identity of the ring R mod I of x. So third property also satisfies. So we have nothing to prove. So since f of 1 is equals to 1 plus I, f is a ring homomorphism. So we have proved that this function Rx from Rx to R mod I of x is a ring homomorphism. Now let's see its onto. Ontoness is also clear. So let's prove f is onto. So let's take an element a0 plus I plus a1 plus I plus an plus I of x power n belongs to the ring R mod I of x. So what will be the pre-image of this element? So naturally you can see that if we take the polynomial a0 plus a1x plus an x power n, then this is a polynomial in the ring R of x, right? And image of this polynomial is nothing but a0 plus I plus an plus I x power n. So every element has pre-image. So f is onto. Okay, so f is a surjective homomorphism. Now what will be the kernel of this map? Because if we use the first isomorphism theorem, so hence by first isomorphism theorem, Rx mod kernel of f must be isomorphic with R mod I of x. So the final task is to determine the kernel of this function f. So kernel of f, so by definition it is all those elements in Rx, means all those polynomials in Rx whose image is 0, such that f of a0 plus an x power n is 0. But 0 means it's a 0 polynomial in this ring R mod I of x. So it should be 0 plus I. So we can write this one as a0 plus an x power n belongs to Rx, such that a0 I plus an plus I times x power n is equals to 0 plus I. Now just compare the coefficients of x power I from the both sides. So then what you will get, it is the set of all those polynomials in Rx such that ai plus I equals to 0 plus I for all I. So this polynomial is 0, that means all the coefficients must be 0. So that is what I have written. Then it is a0 plus an x power n belongs to Rx. So all those polynomials in Rx such that the coefficients are from I. Now this is exactly the set I of x. If you can recall the definition, then this is our I of x. So we all know that kernel of a ring homomorphism is an ideal. And here our kernel is I of x. So I of x is an ideal. And in fact, Rx mod I of x is R mod I of x. Hence, Rx mod I of x is isomorphic to R mod I of x. So we have proved both of the conclusion of the first problem. So is it okay, or do you have any doubt in this? Okay, I hope this is fine. So let's see some application of this problem. So just remember that if I is an ideal of R, then Ix is an ideal of Rx, and the quotient looks like R mod I of X. Okay, so from this isomorphism, so suppose I is a prime ideal of R, then can we say Ix is a prime ideal of R? So if I is a prime ideal of R, what about I of X? Is it a prime ideal? Any guesses? So what is a prime ideal? So I I is a prime ideal. So what are the equivalent condition of prime ideals? So I is a prime ideal of R if and only if R mod I is an integral domain, right? So can you use that fact? So using this, can you say something about this question? Okay, so the answer is I is a prime ideal of R. That will imply Ix is a prime ideal of Rx. In fact, this is if and only if. So I is a prime ideal of R if and only if Ix is a prime ideal of Rx. That is because I is a prime ideal of R, that is if and only if R mod I is an integral domain, and R mod I is an integral domain, that is if and only if the polynomial ring is an integral domain. But this polynomial ring is isomorphic to Rx mod Ix. So this is if and only if Rx mod Ix is an integral domain. Now this quotient ring is an integral domain if and only if the ideal is a prime ideal. Okay, is it okay or do you have any doubt in this? Okay, now what about maximalness? So if I is a maximal ideal, what about Ix? So Ix can be a maximal ideal? What do you think? Okay, so I is maximal, right? So an ideal is maximal, that is if and only if the quotient is a field. I hope you have saw this in the lectures. So I is maximal if and only if R mod I is a field. Now if R mod I is a field, then what can you say about R mod I of X? This is an integral domain, but is this a field? This cannot be a field, right? So if this is not a field, then Rx mod Ix can also is also not a field. So if this quotient is not a field, then Ix is not a maximal ideal. So the conclusion is, if I is a maximal ideal of R, Ix can never be a maximal ideal. And that is because a polynomial ring can never be a field. Okay, I have just write down this line. The rest of the part you convince yourself. I hope this is okay. Okay, let's do the next problem. This is a true false type question. So the part A is, okay, let R be the polynomial ring over the integers. Now let me, I will define two ideals. I is all those polynomials with integer entries such that all the coefficient are even integers. Okay, and the second one is, okay, let me write down this statement. Okay, I have defined an ideal I. So first statement is, I is a prime ideal of R. And the second statement is, if we define the ideal J by set of all those polynomials, integer polynomials, such that the constant term is even, means the A0 is even, then this ideal is not a prime ideal. So we have two statements, which one is true or which one is false, or both are true or both are false. So just think for a few moments. So what about the first one? Is it a prime ideal or not? So you can try is true. Can you give an explanation why it is true? So you can use the definition also, definition of prime ideal. to check if an ideal is prime or not. So what is your justification for A that A is true? So what is the definition of a prime ideal? So I, let's say I is an ideal of R. I has to be a proper ideal. So I is a proper ideal of R. Then I is prime. So whenever a product AB belongs to I, then either A belongs to I or B belongs to I. Right? So just use the definition. So for A, let Px equals to summation Ai times x power I, and Qx equals to summation Bi times x power I equals to 0 to m, such that their product Px times Qx belongs to I. So what we need to check, either Px or Qx belongs to I or not. Now this product is in I, then what can you say about the coefficients of the product? Now how the product looks like. So all the coefficients in the product must be even number, right? So from that, can you conclude that all the coefficients of Px and Kx, Qx are even numbers? So from that, it is difficult to conclude, right? So, so what we can do is, so we can use the earlier problem here. So basically, your I is all those polynomials whose all coefficients are even. So I can be written as a0 plus a1x plus an x power n belongs to zx, such that all ai belongs to your ideal 2z, right? Because all ai are even, so ai must belong to the ideal 2z. So this is basically, you take the ideal 2z of z and take adjoint x. So this is your ideal 2z of x. Now, so if you mod out zx by 2z of x, so by the earlier problem, it should be z mod 2z of x, right? Now, z mod 2z is an integral domain. Is an integral domain. So this polynomial ring is also an integral domain. So this quotient is an integral domain. That means the ideal must be a prime ideal. Is it okay? A is in fact true. Now what about B? Do you have any guesses for B? Okay, so B is all those polynomials whose constant term is an even integer, right? So now let's go by the definition. So let Px, as we have taken summation ai x power I equals to 0 to n, and Qx equals to summation bi x power I equals to 0 to m, be two polynomials in Zx such that whose product Px times Qx belongs to the ideal J, right? Now by the definition, if an element means a polynomial belongs to J, then its constant term must be even. Now what is the constant term of this product? The constant term of this product is just P naught times, sorry, A naught times B naught. So it is an even integer. Now product of two integer is even. That means one of the two integers must be an even integer. Or you can phrase it like, so A0 times B0 belongs to 2Z. But 2Z is a prime ideal. So A0 belongs to 2Z or B0 belongs to 2Z. So either A0 is even or B0 is even. So that means either Px belongs to J or Qx belongs to J. So that is the definition of prime ideal. So J is a prime ideal of R. So B is actually false. Is it okay? So in fact, you can prove this part B uh, using the first isomorphism theorem also. So if you recall from the earlier live seasons, I have defined a map from Zx to Z mod 2Z by f of a0. Okay, let me write in this way. F of px maps to p evaluated at 0, and you take uh, the modulo or mod 2. Then I have told you to find the kernel. Then you can check that its kernel is actually the ideal J and F is onto. So by first isomorphism theorem, Zx mod J will be isomorphic to Z mod 2Z. So you can check these facts. So in that case, Z mod 2Z is an integral domain or even it is a field. So this ideal will be a maximal ideal. So you can prove this in this way also. But this is just by using the definition of prime ideal and uses nothing else. So you should know both this method. So I hope you have understood this. Okay, let's move on to another problem. Problem number 4. So let A belongs to Z and consider the ideal, let's say I, generated by A in the ring Zx. And when I, okay, two problem, let me define it as two problems. So first problem is when I is a prime ideal of Zx. And second one is when I is a maximal ideal of Zx. So I hope you have understood the problem. So we have taken an element, an integer. So this is also an element of Zx because Z is a subset of Zx. Then if we take the ideal generated by that integer in the polynomial ring, then when it is prime ideal and when it is maximal ideal. So can you try the first one by using the previous problems or guess any answer? Just use the first problem which I have done. The first isomorphism means the isomorphism in the first problem. So just try the first part when I is prime ideal. So you just need to find out the ideal I. You just need to write I in a proper way. Okay, so so how the ideal I looks like. So I is generated by the polynomial or the constant polynomial a. So that means what? So by definition, it is the set a times px such that px belongs to zx, right? So this is the definition. Now what is this? So this is set of all those polynomials. Let's say a0 plus an x power n belongs to zx such that a must divide all the coefficients ai, because every polynomial is multiple of a, so all the coefficients are also multiple of a, so a must divide all the coefficients. So this is the set of all polynomials whose all coefficients are divided by a. So by using the earlier approach, this can be written as coefficients are divided by ai. That means ai must belongs to the ideal az, right? So this is in fact the ideal az of x. So if we take the quotient zx mod I, this is equals to zx mod az of x. Now using the isomorphism in the first problem, this is basically z mod az of x. So the problem reduces to, so we need to determine when I is prime or maximal ideal. That means when this quotient is integral domain or field. That means when this quotient is integral domain or field. Now can you give an answer? So when this quotient is an integral domain, means this polynomial ring is an integral domain. This polynomial ring will be an integral domain if and only if this z mod az is an integral domain, and if and only if az is a prime ideal. So when az is a prime ideal, so if and only if a is 0 or a is a prime number. Did you got it? Okay. So similarly, I is a maximal ideal if and only if, so when az is a maximal ideal, az is maximal if and only if a is a prime number. This has been done in the lectures itself. So this is just a typical application of the first problem, nothing else. So I hope you have understood it because it is very useful. Okay, let's do another problem. So it is problem number 5. So let R be a ring, okay, then we can take the polynomial ring Rx. Now in this ring, if we take the ideal generated by X, then what will be the quotient ring Rx mod ideal generated by X? So that is the question. So then prove that the quotient ring Rx modulo the ideal generated by X is isomorphic to R. So this is also very useful. So let's write the proof. So again I will use the first isomorphism theorem. So I need to define a map from Rx to R such that it will be a surjective homomorphism and the kernel will be the ideal generated by X. So define phi from the ring Rx R by phi of Px. You just evaluate this polynomial at 0. Okay. So you take a polynomial and Px and just plug 0 at x. So then phi is a ring homomorphism. Let's prove that. So what is phi of Px plus Qx? So we need to write it in the, okay, let Px equals to summation Pi x power I and Qx equals to summation Qy x power I. This is I equals to 0 to m. This is I equals to 0 to n. Okay. Then what is Px plus Qx? This is just sum of the coefficients Pi plus Qi times x power I, and I is 0 to maximum of n comma m. Okay, now let's see the function phi observing addition or not. So phi of Px plus Qx. So if we evaluate this at 0, what will survive? Just the constant term will survive, right? Because we are putting 0 in place of x. So this is basically P0 plus Q0. Now P0 is basically you take phi and apply it on Px. Similarly, if you take phi and apply it on Qx, you will get Q0 only. So this is so this shows that phi preserves the addition. Now in a similar manner, if you take the product Px times Qx and apply phi, you will get P0 times Q0. But this is phi of Px times phi of Qx. So phi preserves addition and multiplication both. And also phi of 1 must go to 1, because if you take the constant polynomial 1 and if you evaluate at 0, you just get 1. So there is nothing to do. So phi is a homomorphism. Now surjectiveness. Surjectiveness is also clear. So for surjectiveness, what we need to prove? For every element of R, we need to show a pre-image. So let R belongs to R. Then take the constant polynomial R. Then the image of this constant polynomial will be R. Right? It is trivial, nothing to show here. So phi is on 2. Now the last part is, okay, let me write it here. So by first isomorphism theorem, Rx mod kernel of phi is isomorphic to R. So we need to determine the kernel. So what is the kernel of this map? So kernel, by definition, it is the set of all elements of the domain ring. Here it is Rx, such that phi of this element is going to 0. Now it can be written as all those polynomial in Rx such that, so what is phi of Px? It is P of 0 and it is 0. So what can you say from here? So you are getting a polynomial in which 0 is a root. So Px belongs to Rx such that 0 is a root of Px. Now if we apply the consequences of division algorithm, then you will get, it is the set Px belongs to Rx such that x divides P of x. So by definition, it is the ideal generated by x. Hence, Rx mod ideal generated by x is isomorphic to R. Is it okay? Do you have any doubt in this? Okay. So I hope it is fine for others also. Now from this, we can easily conclude that so the question is when this ideal generated by x is prime ideal and when it is maximal ideal of Rx. So ideal generated by x is a prime ideal of Rx. So you just use this isomorphism. So ideal generated by x is prime. That means this quotient is an integral domain. That means R is an integral domain. And the converse is also true. R is integral domain means this quotient is integral domain. That means this ideal is prime. So I is a prime ideal of Rx if and only if R is an integral domain. So similarly, you can conclude the maximal ideal case also. So X is a means ideal generated by X is a maximal ideal of the polynomial ring Rx. So when it will be maximal ideal. So this is maximal if and only if this quotient is filled. That means R is a field, and the converse is also true. So ideal generated by is a maximal ideal of Rx if and only if R is a field. So I hope it is okay. Okay, let's do next problem. Problem number 6. Okay, so I will write down two ideals, and we have to find out the quotient rings. So how the quotient rings looks like in those two cases. So find out the quotient ring in the following cases. Okay, so first one is, so your ring is q of x, polynomial ring with coefficients in the rational number, and your ideal is all those polynomials a0 plus dot dot a n x power n in R such that sum of all the coefficients is 0. Okay, so sum of all the coefficients is 0. And second one, you take the ring as zx and take the ideal as all those polynomials in zx such that this alternating sum a0 minus a1 plus a2 dot minus 1 power n an is 0. So you have two rings and two ideals, and we need to find out the quotient. Okay, let's put this I also so that it will be uniform. So we need to find out the quotient R mod I. So how this quotient looks like? Can you identify this quotient with a known ring or with a simpler ring? So try the first one. Think for it for few seconds. Quotient rings. Okay, any guesses for the first one or any idea how to do it? Can you guess what will be the R mod I in the first case? So first task for you is to identify this ideal with a simpler one. Can you identify these ideals with a simpler ideal? Okay, what is I in the first case? So it is the set of all polynomials such that the sum of the coefficients is 0. So can you write it in another way? So this is set of all polynomials. So if Px is your polynomial a0 plus a1x plus dot dot an x power n, then what is your P of 1? Then P of 1 is basically a0 plus a1 plus dot dot a of n, right? So this is Px belongs to R such that P of 1 is equals to 0. Okay, if you are still not convinced, then you can you just try to prove that these two sets are equal. I mean, both are subsets of each other. Just try to prove it. Now define a function phi from R. Okay, let me write q of x to the field q by phi of p of x is just p evaluated at 1. Okay, so then this is task for you, that check that phi is a surjective ring homomorphism. This is not difficult, just you do it by the definition. And surjectiveness is also clear because you can take the constant polynomials. So it is a surjective ring homomorphism. And what about the kernel? Kernel is set of all those polynomials such that phi of px is 0. So that means it is set of all those polynomials such that p of 1 is 0. And this is exactly your I. Now use the first isomorphism theorem. So by first isomorphism theorem, your qx mod I is isomorphic to q. Okay, so your quotient is exactly looks like Q. So did you got the idea? Okay, so I hope this is fine. Now, what about B? Now, can you identify this ideal with something known? So, this part is exercise 4. Okay, now let's come back to part B. What about I in this case? Can you write it in a simpler way? So, in B, your I is set of all those polynomials in ZX such that the alternating sum of the coefficients is 0. So if you take Px as the polynomial a0 plus an x power n, then what about P of minus 1? This is basically, you just plug minus 1 in place of x. This is a0 minus a1 plus minus 1 square. So it will be plus a2 plus dot dot. Uh, okay, this is x power n. So an x minus 1 power n. So this is minus 1 power n an. So your I is basically set of all those polynomials such that p of minus 1 is 0. Okay. So now you just use the same idea and define a ring homomorphism from zx to z by evaluating at minus 1. So define phi from zx to z by phi of px is p of minus 1. Then similarly you can check that it is a surjective ring homomorphism. Then phi is an onto ring homomorphism. This you can check, and the kernel is I. So this is also you can check. So this will follow by the same way as we have done in the first part. There is nothing to do. So the main task here is to identify these ideals with a simpler version. So here zx mod I is isomorphic to z. Is it okay? Okay. So okay, then let's move on to another problem. So so we have saw the ring of Gaussian integers z of I, right? So it is an infinite ring. Now, so if we take an element, let a plus ib belongs to z of I, okay, and take the ideal I generated by this element. Then the problem is, so if we take the quotient z of I mod the ideal I, then it will always be an finite ring. So then, so that this quotient is a, okay, we need to take a non-zero element. So let this is a non-zero element, because if it is zero, then it will be z of I. So that is not a finite ring. So it is a finite ring. So if you take a non-zero Gaussian integer and go modulo by that, uh, modulo by the ideal generated by that element, then you will always get a finite ring. Okay, so how the elements in this quotient ring looks like? First, try to see that. So z of I mod the ideal generated by a plus bi. So this is basically some x plus iy plus I, such that x comma y are integers. Right. This is the definition of the quotient ring. So we need to, because this is collection of cosets, so we need to prove there are only finitely many distinct cosets to prove that it is a finite ring. So how can we do that? So now observe that. So the idea is x and y are in z, right? So if we can prove that this x and y has only finitely many choice, then we are done. Because if x and y has finitely many choice, then we will have only finitely many cosets. So that will be our target. So observe that uh, now a plus ib is in the ideal I. So any multiple of this will also in the ideal I. So a plus ib times a minus ib is also in I. Now what is this product? This is just a square plus b square, and this is in I. So this integer is in I, means any multiple of this is also in I. So this means a square plus b square times x plus iy also belongs to I for all Gaussian integers. Now this means what? This means a square plus b square times x plus iy plus I is equals to 0 plus I. Right? That is by the properties of quotients. So this is the multiplication in the quotient ring. So this says if we multiply a square plus b square with any quotient, it will give you the zero quotient. So in place of x plus iy, we can just take the element 1, means the identity multiplicative identity of the quotient ring. So a square plus b square times 1 plus I is 0 plus I. So this says, so x plus iy plus I belongs to this quotient uh, z of I mod a plus ib, that will imply x uh, is in the set uh, 0 1 up to a square plus b square, and similarly for y also. Because all other terms can be written in the same I want to say that all other cosets will be fall in this coset itself. So both x and y has finitely many choice. So all these elements has finitely many choice. So this quotient is a finite ring. So whatever you take the element, it must be non-zero. Then you take the quotient ring, then it will always be a finite ring. So I hope this is okay for you. Is it okay? Or do you have any doubt in this part? Okay, I hope this is okay. Okay, so let's do another problem. So, so, I have done some problems on quotient rings. First isomorphism theorem, prime ideal, maximal ideal. And, okay, let's do some on correspondence theorem. Okay, so problem number 8. So I hope you can remember the correspondence theorem. So let R be a ring such that the cardinality of R is let's say 50, and let's say I be an ideal of R, okay, such that cardinality of the set I is 10, okay. Then so that I is a maximal ideal of R. Okay, so you have a ring, finite ring whose cardinality is 50, and an ideal whose cardinality is 10. Then you have to prove that ideal is a maximal ideal of R. So let us recall the correspondence theorem. If you have a ring R and if you have an ideal I, then you can take the quotient ring. Then the correspondence theorem says if you take the ideals here, ideals in R mod I, you take the set of ideals, then there exists a bijective correspondence from the set of all ideals of R which contains I. So in the left you have all ideals of R which contains I, and in the right you have all ideals of R mod I. Then you have an uh, bijective correspondence. That is the correspondence theorem. So we will use that theorem here. So we need to prove I is a maximal ideal of R. Now what is the definition of maximal ideal? So if you take another ideal such that I subset of J subset of R, then either J equals to I or J equals to R. That means in between I and R, if there is no other ideal, then your I is a maximal ideal. So that is what we have to prove here. So let J be an ideal of R such that I is proper subset of J and it is subset of R. Now to prove I is maximal, we need to prove that J is equals to R. So we need to show J equals to R. Now J is an ideal of R which contains I. Now J is an ideal of R such that J properly contains I. So this implies J mod I is an ideal, in fact it is non-zero, is a non-zero ideal because J is not equals to I, non-zero ideal of R mod I. So this is by the correspondence theorem. Okay, now uh, what is cardinality of R mod I? Now cardinality of R mod I is cardinality of R mod cardinality of I. So this is 50 divided by 10, which is 5. Now this is an ideal. So this is a additive subgroup of R mod I. So order of J mod I must divides order of R mod I. So this is by Lagrange's theorem of groups. Now this cardinality is 5. So cardinality of j mod I divides 5, and 5 is a prime number. So cardinality of j mod I is 1 or 5. But uh, j mod I is non-zero ideal, right? So it contains uh, more than one element. So its cardinality cannot be 1. So j mod I is cardinality of j mod I is 5 because j properly contains I. But cardinality of R mod I is also 5, and this is a subset of R mod I. So j mod I is equals to R mod I because j mod I is a subset of R mod I and cardinality of both sets are same. So j is equals to R because their cardinality are same, because cardinality of j is equals to cardinality of R. So we have started with an ideal j which properly contains I, and we have proved j is equals to R. So in between I and R there are no other ideals. So I is a maximal ideal. So hence I is a maximal ideal of R. Is it okay? Okay. Okay, let's do another problem. So this is a true false type question. So you consider the ring Q root 2, and this looks like A plus B root 2 such that A and B are rational numbers. Okay, so let's put a name and Q root 5 defined like uh, A plus B root 5 such that A and B are rational numbers. Okay, then the statement is then Q root 2 is isomorphic to Q root 5 as ring. So they are saying that these two rings are isomorphic. So you need to check this is true or false. So think it for few minutes. So are they isomorphic? Okay, so let's try to see if they are isomorphic. That means if there is an isomorphism between these two rings, then what happens? So let f from q root 2 to q root 5 be an isomorphism. Okay, so if they are isomorphic, then according to the definition of ring homomorphism, one must go to one, right? Then f of one must be equals to 1. So that means f of 2, which is f of 1 plus 1, which is f of 1 plus f of 1. So this is also 2. Now, what is f of 2? This is basically f of root 2 times root 2. Now, f is also multiplicative. So this is f of root 2 times f of root 2. So this is equals to f of root 2 whole square. So this means f of root 2 whole square, which is equals to f of 2, and this is nothing but 2. So f of root 2 must be equals to plus minus root 2. But your root 2 does not belongs to this set q root 5. That is something you can check. This does not belongs to q root 5. So you just try to prove it. So try to prove this. Root 2 cannot be written as a plus b root 5, where a and b are rational numbers. If you can prove this, then you will get plus minus root 2 does not belongs to this. So this map is not well defined in fact. So this is a contradiction. So there cannot be any isomorphism between these two rings. Hence, q root 2 and q root 5 cannot be isomorphic. Okay, I hope you have got the idea for this. Okay, one more easy problem related to this isomorphism. You consider the ring of all complex numbers C and consider the ring of all real numbers. So are they isomorphic? So so the statement is C and R are isomorphic as rings. So is it true or false? So it is true or false. So this is easier than the previous one. Try to think it. Yeah, any answers? Are these two rings isomorphic? No. Okay. So, what is your justification? So, why they can't be isomorphic? Okay, so let phi from C to R be a ring isomorphism. Be a ring isomorphism. So then phi preserves addition as well as multiplication. And also the for a ring R, so recall that if you take a ring R and take all the units, then this is a group with respect to multiplication of the ring, right? And a ring homomorphism take units to units, means it maps unit to units. So then phi restricted to group of all units of C to group of all units of R is a group homomorphism with respect to, okay, it's just a group homomorphism. So for a ring R, R cross is the group of all units of R. So this is something which I have proved in the first problem solving season. If you don't know, you can go back and take a look. So since phi preserves multiplication and phi maps units to units, so phi restricted to C cross is a group homomorphism. But in C cross, so C cross is basically your C minus 0, right? Because C and R both are fields. So every non-zero element is a unit. Now these are groups with respect to multiplication. But in C minus 0, there are elements which has finite order. Uh, let's say I. So then, so now uh, order of I with respect to multiplication is 4. But order of phi I cannot be finite. Because in R star, there are only two elements which has finite order and which are 1 and minus 1. But phi maps 1 to 1, so it maps minus 1 to minus 1. And it is also bijective because it's an isomorphism. So phi of I, it cannot be plus minus 1. So it cannot be of finite order. So this is a contradiction. Because in a group homomorphism, order of phi I must divide order of I. Right? You just go back your group theory course. So order of phi I must divide order of the element I. So this is not happening here. So this is a contradiction. Hence, C cannot be ring isomorphic. Okay, cannot be isomorphic to R as rings. Is it okay? Do you have any doubt in this? So I hope it is okay. So let's do one more problem. Okay, so let R be a ring such that for every element, let's say A in R, there exists an integer, in fact positive integer, let's say n greater than 0, and this integer will depend on A also. Let's say depends on your element A such that A power n is equals to A. So for every element A, there exists a corresponding integer n such that A power n equals to A. So you have a ring with this property. Then so that every prime ideal in R, every prime ideal in R is a maximal ideal. So we have saw rings in which uh, there are prime ideals which are not maximal ideals. Like you can take the integer ring of integers. There the zero ideal is prime but not maximal. But if you have a ring with this property, then every prime ideal has to be a maximal ideal. Okay, so let's prove this. So we need to prove every prime ideal is maximal. So let's take an arbitrary prime ideal. So let P be a prime ideal of R. So we need to prove P is a maximal ideal. So we need to prove in between P and R there cannot be any other ideal. Right? Now suppose J is an ideal of R such that P is a proper subset of J and J is contained in R. So to prove P is maximal, we need to prove J equals to R. So we need to prove J is equals to R. So this is by the definition of maximal ideal. Now P is a proper subset of J. Since P is a proper subset of J, there exists an element A belongs to J which is not in P, right? Also, by the given property, for every A there exists n such that A power n is A. So use this. So now there exists n greater than 0 such that A power n is A. Now this implies A power n minus A is 0. This implies A times A power n minus 1 equals to 0. Now since P is an ideal, so P is a subgroup under addition. So it contains the 0 element. So 0 belongs to P. Now 0 equals to this element. So A times A power n minus 1 belongs to P. But P is a prime ideal and this product is in P. So either A is in P or this element is in P. So this implies A belongs to P or A power n minus 1 belongs to P. But we have assumed A belongs to J minus P. So this cannot be true. So this implies A power, okay, this is because P is prime. Okay, A power n minus 1 belongs to P because A does not belong to, okay, A belongs to J minus P. Now P is a subset of J, right? So this element belongs to J. So A and A power n minus 1 belongs to J. That will imply A power n minus 1, comma, A power n minus 1 belongs to J. So this will imply uh, A power n minus 1 minus A power n minus 1 also belongs to J because it is a subgroup under addition. So that will imply 1 belongs to J. Now 1 is a unit. If a unit belongs to J, then that ideal has to be the whole ring. So that will imply J equals to R. So we have taken an arbitrary ideal which properly contains P. Then we have proved J equals to R. So this proves P is a maximal ideal of R. Thus, P is a maximal ideal of R. So, is it okay for you? So did you got the proof? Okay, so I hope it is fine. So do you have any other doubts? Okay, so if you have no other doubts, then we will wrap up today. Okay, then. Okay, thank you then. Thank you for joining.
Thank you, sir.